Hi. In this video, we will simulate the response of an unbalanced simulation of the pendulum model and compare with the actual result logged from the pendulum setup. So this model you have seen in the previous video where we have simulated the response of pendulum decaying model response with its length and weight model. So the 30 grams and 210 was the length and that was the friction model coefficients. Now let's say I have to record the same response of the pendulum vertical arm, which would be dropped from the angle of 90 degrees. Then we need to record and see how does it behaves. For downloading and model, so I take a gain block or attenuate block for the first. Okay, a gain block and an attenuate block. I just add a dummy input like constant and single monitor. So we will record the encoder output of the vertical arm and we will divide it with attenuation count. So the attenuation count of our vertical encode is 10,000 and we will multiply this by 360 degrees so that we get the count values in degrees, the revolution in degrees. We select this model and say implode. So this model will be downloaded. I rename this model as vertical arm vertical log. Okay, vertical arm log. So let's download this. So I just start simulation. I go to tools, real-time toolbox, C code generation, select the 20sim4C template and look for the vertical log model. Say okay. It will say that I want to create a project. We will open a 4C tool chain. Select the target template as rotary inverted pendulum setup. Click on OK. So you can see the board is connected through the LAN network. Now connect the input. We need to connect with the vertical arm this time, and the output we will not connect to anyone. So we just drop it to an LED and compile it. So you can see the compilation is over. So you just go to command window and say apply. So the settings are good, 500 Hertz. This is the value you should see over here. Now we go to log and in the background you can see the pendulum setup. So we have installed the horizontal shaft with the vertical arm, this one, okay, as the vertical arm. Now we need to record the attenuate input. In case anything goes wrong, I can at least record this input value and the final gain output. Now let's say apply and start logging. Okay, so I start with 0 and I'm going till 80, so that should be sufficient. Let's start recording. So you have to lift the arm and just drop it. You have to take a help of any of your assistant to hold the horizontal shaft so that it do not swings while you are logging this values. You can see at the background the green LED is blinking, so whenever it is crossing the 0 mark, the green LED will blink, but we won't be using those response. So you can see the vertical arm is swinging quite well. So it is almost at its ending stage. So you have to make sure that you run at least more than 80 seconds, because here you can see in the log files it has recorded till 72 seconds. Yeah, so you can see that the oscillation has stopped and the logging is over. So you can see the plot coming up, and this is how the response are coming. So you can see this is the input, that's why you see high number of counts. But you see in the pink one, that is our output response. So we can log this and start comparing with the simulation. So I just save this file as vertical response. Now let's close the 4C toolbox. Come back to this. Now I remove this constant input and put as data from file. There you go. And I double click on this and browse to the C drive temp folder 20sim4C and vertical log vertical arm response, and I'll take only the input one, not the output, because already in that sum model I have those blocks present over there, so they will reproduce the same response. So this is the input of this, so I can just go inside and they will attenuate and give me the same response. So I can just add that response to it. So I say angle curve, single monitor, and I can say this is angle measured. So there you can see the response of it. The only you can see a time shift, that is because we started at a different time and the simulation is starting from 0. So I just split it and I double click on the pink line, and you can see that it starts from and it drops from here. So you can again zoom to a particular area, and so you can start somewhere from here. It's 97 or maybe 98. Okay, maybe 98.028 is the value. So that is startup. Okay, so I just open a notepad for remembering the values. So I just copy the X value, and in the notepad I just make this. So that is my X, and the value of over the angle drop was 98 point something something, this value. Okay, so I have to start the simulation model from this point. So I just copy the X value, I just copy this, and I open the run properties and ask him to start from the same 4.52199 something. Okay, or maybe 22. So this is 22. This is easy to remember, 4.522. So there you can see that I have started from that corner. So only difference is the differences are like this start from 88 and this starts from 98.02. So we have to add that degree in the simulation model. So the initial value, you can see that both of angles were different. So this is 98, this we were starting at 98.02. so I've adjusted the initial radian value so to give a close value. So here we are also going to start from 98.02. okay. Yeah, so there are 3 steps, 2 values extra, that's okay. So you have to adjust this initial value to get the same angle. So if you are having a difference, you have to change this initial phi so that you get the same starting value of angle which is being dropped for the pendulum. Now when you compare these two results, so you find that both are close to each other, but still they are not matching 100%. So the user needs to adjust the friction model to get the similar response. So maybe I just play with the top value and slightly decrease it. So you can see the response of the simulation model is increased. Now it is happening at a different time. Take this to 450. This decays too fast. So this, I take it to 420. So it's coming closer. Yes, much more closer. Yeah, so in this model you can see that the response is quite close. Somewhere at the amplitudes are different, but for that you might have to change the other coefficient like rotational frictions and make it 100. So yes, then it matches. So it's a different permutation combination of the friction model where you will get the best accurate results. So I just set it back to 95 and see the response of it. Yeah, so it's coming very close. The user can also take help of the Fourier analysis, so frequency domain toolbox, FFT analysis, and thereby you can see the comparative results of both FFT of both responses. So this is how the users can repeat the same pendulum model. Thank you very much.